All right, folks, it's Bass Action back in action here. We are on our second day of section 1.3, and on this page of our notes, we're going to look at the Pythagorean Theorem and the distance formula. And the big idea that I want you to walk away from on this page is to recognize that the Pythagorean Theorem and the distance formula are essentially the exact same formula. All right, let's jump into the Pythagorean Theorem first. Some of you might already have seen the Pythagorean Theorem before, but I want to cover a few things that tend to get a little bit lost. So the first part here is under our Pythagorean Theorem, it says in a right triangle. It's very crucial that we recognize that when we're talking about the Pythagorean Theorem, we're talking about a right triangle. In fact, if we're talking about the hypotenuse of a triangle, we're automatically talking about a right triangle because no other type of triangle has a hypotenuse. So in the Pythagorean Theorem, it says that if A and B are the legs and C is the hypotenuse, then A squared plus B squared equals C squared. Of course, we can reverse this equation oftentimes. We can say C squared equals A squared plus B squared, which is how I often say it. Now, the hypotenuse, to find the hypotenuse is always going to be across from the right angle. That's why you can't find a hypotenuse in any figure that's not a right triangle. So if we're looking for our hypotenuse in this triangle, we find the right angle and we go across, and that value, whatever is there, variable or number, has to go in for C. So let's jump into an example here with the Pythagorean Theorem. It asks us to find AB. Now we'll notice when we look at the picture that AB doesn't have a variable on it. There's no variable in the picture, so we can put a variable on AB for us. Now we can use our Pythagorean Theorem to solve for x. We're going to find the hypotenuse first, and we're just going to plug in. The hypotenuse squared is going to equal the sum of the squares of the two legs. Now, quick algebra, I'm going to show more steps here because we haven't done these before, but as we get through this process, we will be able to skip a few steps. So this is going to give us an x squared equals 48. You'll notice I moved my variable to the left just because mentally that makes it a little easier for me. I'm going to take the square root of each side, and in the process of taking the square root of each side, I'm going to simplify the square root of 48. Now, if you happen to be using a calculator that just simplifies it for you, I do need you to make sure that you can simplify this without your calculator, without a button that just simplifies it for you. And I'm going to break 48 down to a perfect square of 16 times 3. So that means that the length of x is 4 radical 3. I'm going to put a u on there for units. If you remember from your algebra classes that when we take the square root of each side of an equation, we get a plus or minus here. That's true, but in our case, our x is the length of that side, so we're not going to have that negative value because the side of the triangle can't be negative. Okay? So let's go on to another problem. In the next problem, we want to find CD. So we're going to find the length of CD. So I'm going to put an x on CD. I'm going to find my hypotenuse, and this time my variable is the hypotenuse. So I'm going to have my hypotenuse squared, and then I'm going to have my 9 squared, and I'm going to add to that my 3 square root of 5 squared. Now, this problem is more challenging because we have to remember how to square that radical. So I'm still going to have an x squared. I'm still going to have an 81, and you'll notice I'm leaving a little bit of a gap here because I want to write something out. This 3 radical 5 squared means 3 radical 5 times 3 radical 5. So that means I'm going to have a 3 times 3 is a 9, and a square root of 5 times square root of 5 is 5. So what I really have is a 9 times 5, or in other words, 45. So that means I have an x squared is equal to 126. I'm going to take the square root of each side. I'm going to simplify the square root of 126. The perfect square that goes into 126 is 9, so I'm going to have 9 times 14. So my length of x, or length of CD, is 3 square root of 14 units. All right, so that's our Pythagorean theorem. The most challenging things on that are making sure that the hypotenuse always goes in for C and squaring radicals. Now let's move down to the distance formula. This is a commonly forgotten formula, but if we think about it in terms of Pythagorean theorem, it becomes a lot easier for us. So let's take a look at a concrete example first. If I'm asked to find the length of this segment right here, what I can imagine is a triangle drawn in this coordinate plane. And if I imagine the lengths of those triangles, I can imagine that I can count out physically that the length of this side is 6 and the length of the other leg is 2. In which case, I can do Pythagorean theorem. X squared for the hypotenuse, 36 plus 4. So my x squared is 40. Square root of each side. X is going to break down into 4 times 10 because that's my perfect square. X is 2 square root of 10. Now, let's apply that exact same idea to the picture that I have over here to the right where I don't have a grid that I can count. So what I'm going to first do is I'm going to name my points. I'm going to call this point x sub 1, comma, y sub 1. The notation gets a little complicated there because the comma and the ones look the same sometimes. And then I'm going to call this x sub 2, y sub 2. I want to find d, or the distance between them. Now I'm going to imagine this triangle, so I'm going to make this dotted. I'm going to imagine this triangle in here, just like we had on the previous example. If I wanted to find an expression for the length of this leg, it would be the difference between these two x values. Similar to what we did here, the difference between 7 and 1 was 6. So I'm going to write that underneath here. I'm going to say x sub 2 minus x sub 1. The same thing happens on the other leg. It'll become y sub 2 minus y sub 1. If I want to find that length, think about what we did over here. That length, besides just counting 2, was the difference between 5 and 3. That means that we can write the formula for that distance as the hypotenuse squared, and each of those legs are going to be squared and added together just using our Pythagorean theorem. And then the distance itself, if we finish that off, is going to be the square root of that entire expression. So oftentimes what students forget is they forget the fact that these should be subtraction, that the distance formula is subtraction. But if you just think of how you would have done this on a coordinate plane in the Pythagorean theorem, you'll be fine. So let's just do a quick example here. So on our quick example that we've got, I want you to find EB. Now when it says find EB, that notation without the bar on top means length or the distance. So we're going to use our distance formula. But remember, it's not much different than the Pythagorean theorem. I'm going to do the difference between my x values. So I'm going to say it doesn't matter which one is the first point, which is the second. So 4 minus a negative 12 is 4 plus 12. Add that because we add the sum of the squares of the legs. And then I'm going to do negative 7 minus 5, and I'm going to square that. So 4 plus 12 is 16, and then I'm going to square that. That gives me 256. Negative 7 minus 5 is negative 12, and when I square it, it becomes positive. So I have 144. So my distance is going to be the square root of 400, which turns out to be a nice perfect square of 20 units then. Okay. So that's all that we have on distance formula. I do have a reflection question here of a commonly missed question. I want you to think about why does the quantity 4 radical 5 squared not equal 20? And then think about why we're subtracting the x or the y values for the distance formula, but we add them for midpoint. Do a little compare and contrast.